Alright, in today's demonstration, I'll be showing you how to do parallel plate capacitors, yeah? Now, if this is along the lines of the more easier experiments or demonstrations, so you'll probably have a more um, fun time doing all of this, yeah? In this experiment, we are going to model a parallel plate capacitor. Now, a parallel plate capacitor has two conductors in parallel to each other, as the name suggests, and one of the conductor is going to be excited with a voltage. It could be anything. We will give around what, 5 volts or 3 volts, 3.3 volts, anything. So you're exciting it with some voltage. The other conductor is grounded, right? And the space between the two conductors is filled with a dielectric. Now, a dielectric, you could keep the dielectric to be air, to be anything else, but in this experiment, we'll be modeling with molybdenum disulphide. It has a relative permittivity of 7.1. This becomes important later on in calculation. Now, what are the calculations? The calculations are just this, that capacitance is equal to the area divided by the distance between the two parallel capacitances, two parallel plate conductors, sorry, and then you multiply that with the the permittivity of free space times the relative permittivity. Now the permittivity of free space is a constant which is equal to 8.85 times 10 to the power negative 12. You have to remember this. Now the ER for molybdenum, as I've told you, is 7.1. So you can basically theoretically arrive at what the capacitance is going to be, and you could check how that's modeled in the software. That is what we are going to do. We are going to add two physics, right? Now, physics-wise, we will add the electrostatic physics and the moving mesh physics. I'll tell you why we're doing both of these in just a moment, but I want you to look at the deliverables. We'll be doing the surface voltage plot and the surface electric field plot. These are automatically generated, so you don't have to do anything, but you only have to manually do these two plots. This is a 2D voltage plot which looks something like that, and the decap versus the capacitance is nothing but the relationship between the capacitance and the distance. It's a linear relationship. No, you see that they're inversely related, so you want to model that inverse relationship as a graph. So these are the four things you want to arrive through this experiment, and you're going to model these parallel plates. They're going to be modeled to 200 times 200 times 20 mm. These are the dimensions, and I think that is about it. And this is the fifth experiment, right? So we will just start with our demonstration. We will be using the model wizard again, and this time I'm going to be selecting the 3D space dimension, and I will add now if you can't find it in recently used, you can go to the AC or DC option, and there's an option for electric field. Under that you see there's an electrostatics option. You want to click on that and click on add, and now you want to select the moving mesh, right? I can just search for moving mesh, and you see in moving mesh, now if you can't directly find it there in mathematics under deform mesh, you could find moving mesh. You just have to select moving mesh and click on add for that as well. Once you've added both electrostatic and the moving mesh, you click on the study option. Now for study, we just want to select the stationary study. You don't need anything else except the stationary study. We will first start with creating the parallel plates itself. What's the first step you do? You make sure that the length unit is set to millimeters, right? And I go to geometry here. I select the primitive block here, and then I do 200 times 200 times 20, right? And I don't have any offset for the first block. I can label this block. Now to label, you can press on the block and press F2, or you can right click on it and there's an option to rename here, right? You don't have to rename. This is only to like make it look more better. I can call this plate 1, okay? And then I can click on another block to add another block. The same dimensions, it's 220 and no, 200, 220, but this time you want to offset it. No, now you want to look at this plane here. I want to offset in the z axis here, right? Because I want to place this plate over this plate, and to do that I want to offset for the thickness, which is 20. So I offset in the z dimension up to 20, and I click on build all objects. You see there's another plate that's created. I'll rename this plate to be called the dielectric. You don't have to once again rename this. I'm just doing this to like make things more clear. You don't have to rename it, okay? Now the third plate is also going to have the same dimension, but you're going to offset this time not for 20 but for 40 because we are always starting from the origin. So I'm going to offset it for 40. And yeah, that's about it. I'm going to build all objects, and I can rename this again to plate 2. Cool. Now I have done 3 plates. Now these two are what our parallel plates are. This middle things are dielectric. No, we will add materials, and it will become very clear what I'm doing with this. When I go to materials now, double click on add materials. You see, I want to add polysilicon. I didn't think, I think I didn't mention it here, but these plates, no, I want to make these plates polysilicon, these 2 plates, and this is obviously molybdenum disulphide, no. So polysilicon, I'll double click on it, and you see it's added to the materials, but it's added to all the 3 of them. But I don't want it to be added to the center, no. Center is molybdenum disulphide, so I remove it from the center. It's only added to the top and the bottom. Now I search for MOS2, molybdenum disulphide. You see this molybdenum disulphide, I double click on that, and I add it to the center one. Now, if you go to polysilicon, you see the relative permittivity is already added. But for molybdenum disulphide, the relative permittivity is obviously not already added. Now, to add relative permittivity, because your solver won't be able to solve if it doesn't know what the relative permittivity of molybdenum disulphide is. Now, to add that feature, you have to go to material properties. You have to go to basic properties here, and you have to look for permittivity, right? You see there's an option for relative permittivity, not permeability. You have to make sure it is relative permittivity. You right click on it and you add it to the material. Now you can go to the basic properties of the material. You see there is relative permittivity added. I want to make sure that this is 7.1 because the relative permittivity of molybdenum is 7.1. So once you have made sure of that, you have basically created the parallel plate, the dielectric, and the materials are properly assigned, right? You can now, what you can do is you can go to the moving mesh option, and you make sure only the center mesh is created as moving mesh. Now moving mesh, what it does, see, we're trying to sweep the top block up and down, no, to check the, you're varying the D gap to check the capacitance, but when you do that, the center block will get deformed. So the mesh itself is getting deformed and you get some error. Moving mesh basically tells the solver that, look, you're expecting the center mesh to deform, and that's okay. Just remesh it every time you compute. So that is what it does. That is why you have to mesh the dielectric, because you're moving the plate 2 up and down. Fine. And to move the plate 2 up and down, what you have to do, you have to set a parameter. No, you have to set a parameter called D gap. And initially I want my D gap to be 40 mm. Why? Because what is the initial offset for my plate 2? It is 40 mm, right? So my plate 2 should be 40 mm initially. I go to plate 2. Instead of 40, I can simply write now D gap. Okay. And I can simply build all. Now if all the plates are set, this is, I've added a variable, I've added moving mesh. Now the linear elastic properties are all defined. Okay. What I have to now define are the electrostatic properties. How do I do that? I have to click on the electrostatic option. I go to studies now, and you see there's an option for boundary and this terminal. Go to boundary or domain. Don't go to boundary, go to domain and add a terminal option. And you'll add the terminal to the top block. Okay. What's the voltage going to be? Since I want to give voltage and not charge, I change this to voltage and I put this around 5 volts, let's say. Okay. You can give this anything, but I'm giving 5 volts. And now I want to add the bottom thing as ground, right? And the way to do that is you go to boundaries, because you can't find ground here. You have to go here and you have to add ground. And I want to add ground to the bottom part, right? I can click on this option here. You see there's an option to toggle transparency. When you click on that, you'll be able to like easily add, if there is any surface in between, you'll be able to easily add it to them as well, like this. So I'll add it to all the corners of the bottom plate only, right? I'm going to add ground to it. Sweet. Now I've added to all the bottom parts. See, you have to add this line also. Okay. I've added to the whole bottom plate. I've added ground. Sweet. Once you've added ground to the bottom plate, I've added excited the top plate. The electrostatic parts of it is completely done. So I've added all the materials. I've added all the electrostatics part, and the moving mesh is also properly added. Now I can start meshing. I click on mesh. I go to mesh, and there's an option for swept mesh, right? I click on that. The size of the mesh, I can make it around extra fine. I don't have to make it extremely fine. I think extra fine will do. and then I can start computing. I go to stationery and I click on compute. It's going to take like it's going to take a minute, to compute. It won't take a lot of time, but initially, as soon as it computes, you see there's going to be two things that come, right? The first thing that's going to come is the electric potential plot. This is the electric potential plot, okay? And the second thing that's going to come is the electric field plot. Yeah, so you have electric potential plot, electric field plot. So these two plots are the first two deliverables I've talked about already. Okay, now since you're done with the first two deliverables, the next two are the 2D voltage plot and the D gap versus C. Now to do these plots, you go to results. I do a 1D plot group this time, okay, and I do a line graph. Fine. When I do that, I can now define a cut line, and I make sure this cut line is going to the center of it, which is already going. Fine. Since that has already automatically been done, I can simply plot for the voltage. You see, it's a Z graph. No, this is exactly what we expected. This is going to be my first voltage plot. You have to draw this plot. Okay, you have to draw that plot like that, and this is our first plot. Fine. After you're done with this plot, the second plot, what did I tell you the second plot is? It's the decap versus capacitance. No, to do that, you have to go to results, add another plot group, because if you use the same plot group, both the graphs overlap. You don't want that. So add another plot group, add a line graph, and what you do this time is you go to this and now to be able to get parameters. Now we have not swept it, we have done basic stationary study, right? Now for decap versus capacitance, you need a parametric sweep. Now to do a parametric sweep, you right click on this, there's an option, right click on the study, there's an option for parametric sweep here. No, just click on that option. Okay, now you can right click on this part here and click on add decap. You see it's giving me options to sweep it. Now I can sweep this decap parameter in meters. Now since I'm doing this in meters and I'm defining everything in I have to be careful of that, by the way. Now range, I'm going to sweep from what to what now. Initially it is 40, no, so I want to sweep from something else. I want to preferably sweep let's say from 30 mm. I want to sweep in 1 mm step, right? And I want to go all the way to 40 mm. I think we can do that. So we can keep the range for that, and I can compute. Now this is what? This is a parametric sweep. Okay. So what it will do now is it will basically, the top block is there now. It will tell the top block to go from 30 mm, one step to 40 mm, and it will give all the results for all those different configurations. With that, we can basically do a D gap versus capacitance plot, right? So we'll just wait a second. We'll just wait for it to finish plotting. And you can also make the range small, then it's going to be much more faster, but make sure that the range is not too drastic, because if your top plate goes outside the block, then it will cause, there are fringing electric fields which come out of it. We're not accounting for it because we have not defined the air domain around the parallel plate, no. So if the displacement is too much, it's not going to account for it properly, and you don't want that. So once I've done the parametric sweep, now you see for different configurations I have different values, alva. Now you can go to the 1D line graph which we created early on. This time what you do is you go for the parametric sweep option, and do for all the D parameters. You can select you can do for all the D parameters, and you can probably do a, actually instead of doing it here, you could also have done it in the global plot. See, line graph marboard, okay, but you can also do, I'll just disable this for now. You can also do a global, you see there's a global plot there under the same results. When you add 1D plot group, there's an option also to add the global plot. You can add the global plot. It also is just as good, but the good thing about global plot is it globally calculates for a given value instead of adding the cut line and all that. It's much more convenient. Okay, so don't do it with a line graph. For the sweep, go to a global plot, and what you can do is make sure all of it is selected for the parametric sweep selection. Click on this add button. And now there is electrostatics. Under that, go to terminals. You see there's an option for Maxwell capacitance, right? Click on that, and nothing. Everything else is already properly set. You can just click on plot. and you should expect somewhat of a linear plot at this moment. And you see it's somewhat linear, it's slightly curved. That's probably because of the mesh, okay? But otherwise it's good. And we're also not accounting for fringing fields, alva. Considering all that, this plot is as linear as it gets, okay? So this is the plot we have expected for it. This is also what we initially predicted we'll get. So that is our plot. What you can do is you can make note of these different capacitance values for different D gap values, and you could compare one of those values theoretically. Okay, that's the whole thing you can do. You can also plot this in a table by right clicking on this, add plot data to table, and then you also get a beautiful table with all the different Maxwell capacitance for different D gap values. Okay, there are 11 values. You can mention some 5 or 6 values and you can call it a day. So these are the 4 plots you have to do for parallel plate capacitors. I hope you could follow along properly. If you have any doubts, you could let me know. But otherwise, this is about it. You just make sure to remember the few subtle things here and there. And I hope you'll do a good job with it. Take care a lot. Bye bye.